Hello, students. Welcome to our lecture on Chapter 3. With this video, we'll cover all of Chapter 3. So with that, Chapter 3 has quite a lot of content in it. If you look through the slides, you'll see a lot of main points. And do please download the slides so you can follow along, take notes, that kind of thing. There's a couple videos that I won't play during this lecture between us. So if you want to watch those are all linked in the slides. So feel free to do it that way. So with that, we'll just jump straight into Chapter 3. As a reminder, if when you're watching these video lectures, if you want to speed them up, it's on YouTube in the bottom right, which to you would be over here, I believe. If I'm pointing to the left, sorry. On the bottom right, there's a little settings button. It looks like a little gear. Click that. You can change the speed to 1.25 or 1.5. Then you can go through the lecture quicker, but just make sure that you're gathering the content, that you're understanding what I'm talking about. Because when I'm speaking at 1.5 speed, it'll sound a lot faster than I'm speaking right now, but you can decide if you can gather the information at that speed. That's usually how I listen to TED Talks, sometimes at double speed. So, but I do miss things when I'm listening to TED Talks at double speed. So it's up to you. Again, all the slides are online. This is Chapter 3. Let's open these slides. Oh, and share the screen. I often forget to do that, which is kind of important. Okay, so here are the lecture slides for Chapter 3. So in Chapter 3, we're going to be covering a lot of different material. We'll go into a lot of depth on neurology and the neuron and how neurons work, because it is very important for a lot of pieces of human development. So the brain, how it works, what different parts of the brain are responsible for is really important for different aspects of development at different points in life. So we'll talk about physical growth in development, motor development, sensory and perceptual development, cognitive, and language. So with that, there will be things in the slides that I might skip over a little bit because there is so much in this chapter. So definitely review the book, read your book, review all the things in the slides. In this lecture video, I'm going to hit all the main points, things that will definitely be coming up multiple times, and a lot of the things that won't necessarily come up multiple times, but are important to know for the future. I mean, all of it's important, so review all of it, but I'm going to hit the very most important of the important stuff. All right, so let's jump into it. As just a preview of the rest of the course, at this point, we're now jumping into infancy. So the rest of the book is basically divided into 2 chapters per time period of life. So infancy, we have a chapter on physical and cognitive development, and then chapter 4 will be socio-emotional development in infancy. And the pattern kind of continues. So chapter 5 will be physical and cognitive. Chapter 6 is socio-emotional, so on and so forth throughout the chapter as we go through the entire lifespan. So let's jump into that. One of the first things in development is that growth happens in infancy in kind of 2 different ways. One is through the cephalocaudal pattern, and that's growing from the head to toe, and then proximal distal, which is from the center of the body outward. So like core, and then to arms and hands and things like that. So that's just a pattern of how infants grow. You'll see their heads grow pretty quickly versus legs not so much, but their core will also grow more quickly than their limbs. So let's talk about growth and how growth happens in infancy. So in our first week, or in our first chapter, we talked about continuous versus discontinuous development. This is an example of discontinuous development. So continuous, as a reminder, is like slow and steady, like you can see a really steady incline and increase in something. So growth, for example, you might, if an infant was growing size-wise, like height-wise, continuously, every day you might see 0.5 millimeter of height growth. But how it actually happens is that it's very discontinuous. There's stages or spurts, growth spurts. You've probably heard that term. So infant growth generally occurs within a single day. So like within a single 24, sorry about that, I hit the microphone. Within a single 24 or 48-hour period, an infant will basically shoot up in size. So they'll grow dramatically within that time period of a day. And then there will be a long time between those growth spurts, say like 15 days or so. So in those 15 days, you won't measure any growth. They won't grow any millimeters. But then just suddenly one day, all of a sudden they've jumped a couple millimeters in size. So it's pretty impressive example of discontinuous growth. Some things in development are continuous, some are discontinuous. Really impressive is that the maximum recorded, so there might be larger growth spurts, but the maximum recorded growth spurt for a single day is 7/10 of an inch in length. So an infant child growing almost an entire inch in a single day. So not growing for like a month, then all of a sudden they grow an inch. That is really impressive to me, really surprising. All of a sudden the baby's clothes don't fit anymore. This is why they had a growth spurt and they grew about an inch. Head circumference as well, 3/10 of an inch, which might not sound like much, but go and measure. So maybe like a doll's head. If you don't have a baby around, you might not have a doll if you don't have a baby around though. I have dolls in my house. So it was the first example that came to my mind. I also have older children, but they don't hold still very well, which is kind of a problem measuring any baby. Anyway, tangent, not important, not going to be on your exam, but yeah, head's growing in circumference. So this way, 3/10 of an inch, pretty dramatic. So the average height of a newborn is 18 to 22 inches long and about 7.5 pounds. They lose about 5 to 7% of their body fat in the first couple days after being born. And so that's mostly just because they're getting used to feeding by sucking, swallowing, digesting, rather than just having it pumped into their body, essentially. So they do practice those kinds of motions in the womb, but they're not actually having to suck, swallow, and digest their own food until they're born. So they lose a little bit of weight, but then they rapidly grow after that. So you'll see a little drop in the first couple of days to a week, and then after that, they will start growing pretty exponentially for a little bit. So about 5 to 6 ounces per week and about 3/4 an inch per month in the first year. So that could all happen within one single growth spurt each month. So it might be 2 growth spurts per month, but it could happen just 1 growth spurt a month. It's pretty impressive. So you've probably seen these kind of growth charts. As you see, they kind of rise up here in head circumference. So with that, a child starts to slow their growth at about 2 years old. So that's this point, the 24-month mark. And at that point, they're about 1/5 of their adult weight. And at age 2, they are about half of their adult height. You can actually get a pretty good assessment of how tall a child will be when they are an adult by taking their height at about age 2. There's also calculators, other variables to add into that and things like that. But you can get a pretty good assessment of how tall a child will be when they're an adult. So for example, we did that with my 2 children, and my daughter is going to be probably about 2 inches taller than her mother and about 3 inches shorter than me. And then her younger brother, will probably be about an inch taller than her and a little shorter than me at adult height. So I'll probably always be the tallest one in this little family, and my wife will be the shortest after the kids become adults. So she's used to that though, I think. With that, let's talk about brain development. This is one of the most important pieces within this course to learn about because it comes up so often. So many pieces of development are cognitive development, socio-emotional development are directly tied to the neural development of the brain. And we'll hit this point many, many times in class. So hopefully it gets into your head. So we do have tens of billions of neurons. And as a reminder, a neuron, hopefully you've read the chapter at this point. So you've reviewed this, you know this material and this kind of a review and new examples. But a neuron is a cell. So any neuron is a cell. Every single one is a cell, and it does cell-like things. Just like any cell, it's trying to live, it's trying to survive, it's using energy, it's outputting things. It has a nucleus, DNA, things like that. So all the normal parts of a cell are in a neuron as well. So a neuron is just a very specialized cell to do a special job of transmitting electrochemical messages. So with that, the brain develops rapidly, both in the womb and then in the first 2 years of life. So in infancy, the brain is developing really rapidly. New neurons are still being created after birth. So that's called neurogenesis. And then about age 2, it kind of tapers off. And except for a few very specific parts of the brain, it doesn't seem like human brains really create new neurons after the age of 2. So there might be a couple specific areas, but we'll get to that when we get closer to adolescent and adult development where we see that happening. So because of that, this is why it's so important to protect babies from falls, because their brain is still developing. The neurons are in the right place, but there's still new neurons being created and then migrating to the place they're going to be. Neurons are not like other cells that like split and divide, kind of like a skin cell or I can't think of another cell that just splits to divide off the top of my head right now. They essentially just are made from stem cells, and at a certain point, our body stops doing that. So protect babies from falls. Do not shake babies, even if they won't sleep or won't stop crying. I mean, as a parent to children, I feel this as well. Like, it's very frustrating. You're very tired. We talked about that sleep deprivation that a lot of parents feel. Don't shake babies. Very bad for their brains. So, and by the second birthday, the brain, the human brain, is about 75% of its adult weight. So that means the density of it and the size of it is about the same as it's going to be through adulthood. And then it slowly grows after that. Other things, other cells are added to it to support and structure it. So how do we study brains in infants? Well, PET uses X-rays, which isn't the best way to study brains, but I mean, before we had other things like MRIs, it was a useful tool. So X-rays are obviously radiation. You don't want to bombard people with radiation because usually they don't get superpowers, they get cancer. So that one's not used as much. MRI is a good one, less invasive, but it does require a patient to be still. If you've ever been around an infant, you know that might be a little difficult. EEG is actually really good. It's an electroencephalogram, and that works really well. You might have seen little diodes or little things put on a head, maybe a little cap with little electrodes on it, and you measure electrical activity that's just under the skull. So that's a good way to see how the brain is working, what areas of the brain are doing things. There's also FNIRS, which is functional near infrared spectroscopy. Spectroscopy. And that works well too for young infants because it's still radiation being pummeled at their head, but it's more similar to if you were shining a flashlight through your hand. So when you shine a flashlight through your hand, you can sometimes see like blood vessels, maybe the bones, things like that. You're using a near infrared light essentially rather than a radiation like an X-ray. So it's still radiation, it's just not a harmful radiation. So that's a good one too. So EEG and FNIRS allow the baby to be moving when it's being done. So that can be a lot more useful to study the brain in infancy. So all these aspects we're talking about are relevant to the brain in infants, but they are also going to be relevant to the brain in adults. So let's talk about the parts of the nervous system, and then we'll talk about the structure of the cell of the neuron more explicitly. So we've got the central nervous system, the peripheral nervous system, which includes the somatic nervous system, autonomic nervous system. Sorry, maybe I need to drink a little bit more coffee before I try these words again. All right, so central nervous system, let's do some better vocabulary. Okay, so central nervous system. We've got this diagram right here. This includes the spinal cord and the brain, and we'll get into the other parts of the brain, like the hindbrain, midbrain, forebrain in a minute. The somatic nervous system and autonomic nervous system. So here we can see that here in the peripheral nervous system. So somatic has sensory and motor nerves. So when you feel something hot or feel something cold, that's coming through your somatic nervous system, then telling your arm to move back from that thing, that is also somatic nervous system. Autonomic is the parasympathetic, coffee isn't working yet, and the sympathetic branch helps to arouse and calm the body. It talks to a lot of different areas that are pushing out hormones into your body and registering those hormones. So like stress hormones, for example. So autonomic nervous system is doing those kinds of things. And these are all connected. They're not completely separate pieces, just as our endocrine system is also part of the nervous system. it's not separate from all these things. So each of these systems has their specific jobs. The brain integrates sight, sounds, touches, temperatures, smells, and messages from various organs. Those messages about what hormone levels are in the body, those go up to the brain and are then interpreted. Brain is also where we do our conscious thinking, where our working memory is happening. And we'll talk about working memory more in another class. Essentially, just quick thing, a working memory is the memory that you're working with literally right now. So as you're listening to what I say, trying to interpret these words, trying to think of what you want to put in your notepad, or as you're typing notes about this lecture, that material that you're working with at this moment is working memory. It's where you consciously live, I guess you could say. You could think of it as a workbench, a table. A good example might be actually the show Inside Out. So those characters in Inside Out, they have that really big table. They have that field of view of what Riley, the character, is seeing. And so joy and sadness and all of those emotions are tapping out things about what's happening currently. The working memory can also pull up memories from the past and interpret things that are happening now and decide what to do in the future. So that's what working memory is. It's the working part of your consciousness that's pulling previous long-term memories and storing stuff that's happening right now. So that's what your working memory is. That was a little longer explanation than I actually intended to give, but now you understand it a little better. But the brain is doing that. So it integrates those experiences, makes memories, finds meaning, makes connections between things. So that's what the brain does, and we'll talk about other aspects of the nervous system. Right now, since we're talking about the brain, I want to jump into talking about neurons. So this is one of the most important things to learn. Definitely will be on your final, definitely be on your first exam as well. So make sure you listen, you review the chapter, you review these slides, make sure you understand. I've got some videos that I'm going to show with you right now. At the same time, you can also you could also look over the other videos that I have included that we're not going to go over during this class time. So there are many specialized neurons, but all of them share these same kinds of characteristics. So they're all cells. So here we see this cell. This is the cell body. So the main part of the cell. There's a nucleus here with chromosomes, DNA, like any other cell. There's things like mitochondria floating around, taking energy to different parts of the cell. And the neurons have very special pieces to them. So cell body, just like any cell body, but they also have this long thing called an axon. This axon is what sends messages to other neurons. So on the outside of that axon, well, at the end of the axon, you can have many axon branches. So think of your axon, think of an axon maybe as an arm. So you might have two arms. I've got two arms, but neurons only have one axon. So I've got one arm sticking out there towards the camera. That looks ridiculous. And then at the end, my fingers are basically these axon branches. So every one of those could touch one more neurons, right? So at the end of this image, each of these little synapses is creating a connection with other neurons. And that's the direction the message or the impulse is being sent. So you could kind of think of it like a wire that's sending a message, and then it can get divided at the end. But there's always only one axon. Alternatively, there are dendrites. Dendrites are the other arms coming off of the neuron, and they receive messages from other neurons. So a dendrite might be connected here at this point with the axon branch of a previous neuron. And so here's the axon branch of one neuron, here's a dendrite of another neuron. So maybe this part of this axon branch is touching, and so the message can come down this neuron and all the way through that axon branch and then hit this dendrite and send that message through that neuron. So these connections of neurons, these networks of neurons, are really how essentially everything that we do is done. So you've got one neuron here, you've got another neuron it's connected to, many neurons it's connected to actually. So cell body, axon, dendrites, myelin sheath. The myelin sheath is this fatty substance. It's actually another cell that's made up of a lot of fat that essentially insulates the axon. That allows it to have a faster transmission speed and have less potential loss of the message through the axon. So neurons are designed in a way that if you take an internet cable, for example, when I got internet into this house, I was quoted my speed would be X megabytes per second. And then when it was actually installed, I wasn't seeing exactly that speed. And so the technician was like, well, why is that happening? And so they traced the line back and they said, oh, it's because you are literally like 50 meters further than that quoted speed. So if my house or if those wires were 50 meters shorter, the message would degrade less so that I would be getting a faster speed. Axons, on the other hand, and cells, they send the message differently. It's not like light going through a fiber optic tube or electricity going through like a copper cable. Those can degrade really rapidly. So these systems in the body, and we'll zoom in on exactly what's happening for that, are made in a way that there is a very, very, very low likelihood of that message being degraded, the intensity being changed, anything like that. So it's really impressive. So that is the basic structure of the cell. This cell might be connected to many, many, many other neurons, or even for a motor neuron, those axon terminals, those branches might be talking to muscle cells. So it might be sending a message down to a bicep to say, do a curl, right? It might be sending a message to any other muscle to activate, to tense up, to contract. All right, so the nucleus, just like other cells, directs the growth and maintenance of the cell. Since these are cells, the nucleus wants this cell to be efficient. It wants the cell to be using the energy that it has wisely. It doesn't want to use too much energy. It doesn't want to take up too much energy. And so that's pretty important for a lot of cognitive things that happen in the future. So neurons are cells. They have to use energy. They have to use resources to run. So if you're not putting those resources into them, your neurons won't work correctly. If you're putting in chemicals that alter the way that they're working, they might work funny. And so we'll get into that later too. So remember that neurons, the individual cells, they want to be energy efficient. They want to use the energy that they need and not use too much energy. It's better for our whole system if our brain isn't using too much energy, because then we would have to eat more. We would have to fuel it more, and that might give us more brain capacity. But if in our evolutionary past, we were not able to get that many calories to fuel it to that point, that kind of mutation to need more energy for your brain would have been selected out. So we're kind of at a balance point with where our neurons have evolved to be, but it leads to some positives and some negatives with our cognition and what we're capable of. Attention wise, for example. So with that, an axon again carries information away from the cell to other cells, whether it be a muscle cell or, in the brain's case, a lot of other neurons. Axons can be up to 3 feet long with many branches at the end. So if you think of an axon going down your spinal cord, that's about our longest axons. For giraffes, they have some axons going from their brain stem all the way down their spinal cord that are like 12 feet long. And that entire time, the way that a cell is designed to send this message, it doesn't degrade the message at all. It's really impressive. So dendrites receive information. So they are receiving the packages of electrochemical data, taking it into the cell body. And then if there's enough of a signal, so they get, it's not actually a spark, like it's not actually an electrical like spark. It's a chemical that's positive or negatively charged. But let's just use the image of a spark. So the end of my pointer here is a spark. It gets it here at this dendrite. It sends it here into the nucleus. That message is kind of paused right here for a minute before, if there's enough strength to that signal, then a message is now sent down this axon. So it receives the message in the dendrite, kind of pauses here, and then will be sent down the axon if there's enough strength to that message. Most neurons have a lot of dendrites, so far more than even this picture shows. So I'll show you some images in a minute of actual dendrites under a microscope and actual neurons under a microscope. It's really impressive how squiggly they look. That's a word, right? Squiggly. Myelin sheath. Said all this. The only point that I didn't talk about was that certain diseases, such as multiple sclerosis and other things, can actually damage that myelin sheath and lead to messages, say, connecting with another neuron that it shouldn't be, degradation of that message that shouldn't happen, neurons and nerves not receiving a strong enough message because the neuron before it didn't have enough myelin sheath. All right, so let's take a look at some cells. Let's first take a look at a human stem cell specializing into a neuron. From this video, it only takes about 14 hours for a human stem cell to become a neuron. It's really impressive, and let's watch that. I will close this, and then we will go to here. All right, this is it. So this is multiple stem cells. Well, as you might have seen, my audio just cut out. I actually kept recording for about 30 minutes after that. So I recorded all the rest of this piece about neurons that you'll see already. And all the audio was screwed up. So let's do that again. Hopefully I change the settings correctly this time. So let's watch that video of stem cells being specialized into neurons, and then we'll watch how neurons actually send messages. So I will share my screen and share the computer audio. That was the main problem last time that got it all messed up. All right, so now you should be able to hear the message or the video as well as me. So at this point, it's about 9 hours into this process, if you look at the time code over here, and you should be able to start to see what kinds of things are happening. So this is becoming a cell body. If you look off of it, it looks like there are other structures around it. These may be axons, or one of them may be an axon. These also might be parts of other stem cells becoming the structural cells that help to hold neurons in place. Similar to how your skeleton is a structure that the rest of your body is kind of built around, neurons aren't just floating by themselves in your brain in just a neuron soup of chemicals. There are other cells within your brain that are basically holding neurons in place. They can also help new neurons migrate to where they're supposed to be. So kind of a skeleton of other cells that neurons are built around, but the neurons are the message sending ones. They're the ones that we focus on. So again, these might be axon, or there might be an axon in here. As it gets a little further along in this process, you'll see what probably are dendrites also being created and then reabsorbed into the cell. So let's watch the rest of that. All right, so now you have a fully formed neuron cell. So from a stem cell. So we're now 18 hours from the time. So less than a day, you've got a stem cell that's become a neuron, which is really impressive. So again, some of these might be structural branches holding that neuron in place. One of them might be an axon. You can see other little things coming off of it. Those are probably dendrites. So that is a pretty impressive process. So let's also watch another video now about what is actually being sent. What are the messages? How does a message go through a neuron? And then we'll draw some pictures, talk about it. Essentially, a message through an axon is happening in a wave. So if you think, so let's use my arm again because it's a useful reference. So you've got the axon here and then the axon branches. As a message travels along, it's kind of like a wave opening and closing chemical gates that change the charge within the axon. So there's chemicals with a charge outside it on this side, and then inside this axon. So inside this axon, there's other chemicals and gates will open and close along the way, kind of in a wave, so that the message stays the same strength the whole way down the axon. So that's one example. We'll watch this better visual example and then maybe draw a picture to try and explain it again in a different way. So let's share that screen. Again, if at any point the audio is funny for you in this YouTube video, you can click and link to this video yourself and watch it. Hopefully the audio does well. If it sounds fuzzy or you can't understand what it's saying at all, watch it yourself and then we'll talk about it in this video.
When you burn your hand results so quickly in an action by your muscles. Many animals respond to environmental stimuli using specialized cells called neurons. A stimulus is detected by sensory receptors and the body responds through motor effectors. These cells working together allow you to respond very quickly to threats. When you touch something hot, heat receptors of a sensory neuron detect the stimuli and send the information of heat to an interneuron in your central nervous system. From there, a motor neuron sends a response from your central nervous system to the skeletal muscles in your arm, causing them to contract and pull your hand away. The fundamental...
All right, so that's a good place to pause and talk about the networks of neurons within our body. So we talked about motor neurons, sensory neurons, we talked about the brain stem, the spine, as well as the brain. So let's see, I want to have the labels up here. There we go. So here on your skin, you've got many, many different types of neurons that are specialized to get pain, pressure, heat, those kinds of things, and then send that message back. So depending on what that message is, it might go all the way back to just your spinal cord and then send a message to your muscles. So extreme pain and extreme heat will just send a message from that limb to the spinal cord back to the muscles to move your hand. And then as you move your hand, it will also be sending that message to your brain. So you actually become conscious of you moving your hand, that it was hot, but your body will do that movement before you're conscious. You literally made no conscious decision to do that. Your body is just protecting you. Alternatively, some messages will be sent all the way to your brain. And then you will cognitively decide with your working memory, what should I do? Should I move my hand? Is it fine? Because I'm just going to be holding this hot pan for another half a second. And then you consciously then send a message down to your arm. So let's look at this in this diagram. You get that pain signal. It comes up this receptor. So it's essentially a specialized dendrite that senses that pain. And then it goes up the axon to this interneuron. So interneuron is a name for all the neurons within your spine as well as your brain. So your central nervous system is made up of interneurons. So this could be a brain cell. This could be one in your spinal column. It could be connecting, again, this branch is probably from this axon is probably connecting to many thousands of other neurons, but we're just simplifying it with it's talking to one right now. So it talks to this in your spine, or you can imagine this in your brain. So that dendrite picks up that message, sends it down its axon. Again, that axon is touching another couple thousand neurons, but in this example, it's just touching one. And so this circuit, you can think of it as a circuit or a network. So if you think of a network of computers, this one is sending a message to this computer is sending a message to this computer. You could think of it that way as well. And then this motor neuron is ending at a muscle cell, telling that muscle cell to contract or not. So those neurons touching your muscle cells are what is telling your muscle cells to flex your bicep, for example. This is actually really neat. If you've ever done any weightlifting, I experienced this really recently. I started working out again recently and lifting weights. And in the first couple weeks, like the first 3 or 4 weeks, I was upping my weight almost every time. A couple pounds, 5 pounds, 10 pounds sometimes. But now I've been exercising for a couple months, and now my weight's rising very much slower. And so one of the reasons for that is actually not because I'm being lazy. I'm actually still working out pretty well right now. It's going well. But the reason my weights aren't raising as much is actually because of neurons. So these neurons can grow new branches, new axon branches. And with that, these motor neurons can talk to more muscle cells. So let's say in my bicep, I have 10 muscle cells. Obviously I would hope there's more than that in anybody's bicep. But just as an example, so let's say there are 10 muscle cells in your bicep. So right here, this motor neuron might only be sending a message to one of those muscle cells to flex. Okay, so we just saw that stem cell, a whole entire stem cell can specialize into a neuron within a day. It's actually quicker to grow a whole new axon branch because you're just growing a new part of the end of this. So let's say I start exercising, I start working out, I start lifting, right? So now those motor neurons are getting more signals than they've got in my example the last couple of years. So because of that, they're like, oh, we have to do more work now. Let's make new axon branches. So rather than just sending a signal to one muscle cell, so let's say my hand's a muscle cell now. Actually, you might not be able to. Let's use the picture. You see that bigger on your screen. So it's touching one muscle cell. I'm now sending more signals saying, hey, I want to lift heavier weights. And so it says, okay, let's make some new axon branches at the end of this. Let's touch more muscle cells. So now I'm touching 3 muscle cells or 4 muscle cells or 5 or all 10. And so because of that, more muscle cells themselves are contracting. And so in those first couple weeks of lifting, you might be able to jump up your weights really quickly, but then you kind of plateau. And some people get disappointed at that point. The reason you were increasing weight so quickly was not actually because you were getting stronger per se. It was because more of your muscle cells are now being activated. Your neurons, your motor neurons are talking to more of them and saying, hey, I need all of these cells to activate now. I need all the motor neurons, or the motor neurons that exist are now telling all of the muscle cells that exist to activate. And so it's not till after that you're actually starting to gain new muscle cells. So because they're breaking down and building new muscle cells, they're getting stronger themselves and dividing and making new muscle, right? So that doesn't happen for a couple weeks. So the first couple weeks when you're increasing your weight pretty dramatically, you might feel really happy about your progress, your weight charting. You're saying, oh, I started at 15 pounds and now I'm at 30 pounds for this exercise. Don't get disappointed when you get to that plateau because your neurons have now adapted. You're talking to all the muscle cells. And now at this point, you are starting to build that muscle. So also one reason people might say, well, why don't I see any visible change in my muscle size? Well, because your muscles haven't quite caught up to growing yet. So really interesting thing. That's how that system of neurons works. Again, there are many, many more neurons within this network, within this system, talking to each other. This is just a really simplified version of it. So let's see what happens at the axon level.
The neurons of the body. Neurons transmit this information through changes in the electrical potential of the membrane. by the movement of ions across the membrane. An electrochemical gradient governs the movement of these ions, resulting in an electrical impulse. The resting membrane potential in a neuron, when the cell is not firing an impulse, is established by the unequal distribution of sodium ions outside of the cell and potassium ions inside the cell, making the outside of the cell more positively charged compared to the inside. The electrochemical gradient is established and maintained by an enzyme called sodium-potassium ATPase. When a neuron is stimulated, sodium ion channels open and sodium ions flow into the cell. This leads to a change in the electrical potential across the membrane called depolarization. The depolarizing electrical potential travels down the dendrites and over the cell body. Multiple electrical potentials will combine at the axon hillock in a process called summation. If the depolarization is large enough, an action potential is triggered. Action potentials are all or none electrical impulses that maintain their amplitude and strength down the length of the axon. The action potential travels down the axon when the depolarization of an area.
All right, so let's talk about what's happening here. There are a lot of different terms. Action potential you should know, but you don't necessarily need to remember all the different chemicals they're talking about. You should hopefully remember sodium potassium ions, but you don't need to remember necessarily ATTP or ATTPase, those kinds of things you don't necessarily have to remember. I do want you to remember the differences in charge. So generally there is a positive charge outside the axon and a negative charge inside the axon. So let's actually rewind this a tiny bit. All right, so this is a little better demonstration. So this is the outside of the axon here. You can see other neurons in the background floating in that neuron soup. And this is one of the sides of the membrane of a neuron. So again, there would be another side of a membrane further down here, but we're only seeing this half of it. So this right here is the inside of that neuron, the inside of the axon. So it's generally negatively charged and the outside is generally positively charged. And so how it's sending a message is that it's not actually sending a chemical itself all the way down this line. So there's no electrically charged chemical like a single electron, kind of like what happens in a power cord or like a copper cable. You don't have electrons literally traveling down this tube. So this is the inside of that tube, right? There's not an electron or a chemical or a molecule traveling down that tube at all. What's actually happening is in a wave, so this gate opens, 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 that kind of thing. In a wave along the axon, it brings in positively charged ions and lets negatively charged ions out. So it changes that gradient, that electrical difference from positive on the outside and negative on the inside. It flips that by opening these channels to let some positive ions, which is just a positively charged molecule, and negatively charged molecules out. So it happens within a wave. If you've ever seen people do a wave, they just, well, that is, I just imagine like that a little clip of me doing that being taken and posted somewhere, and that was embarrassing, an embarrassing thought. Please don't do that. For real, please don't do that. But that's how this is working. They are opening up in a wave. This one opens, then this one opens as the first one is closing, and so on and so forth. So as the next ones down the line open, the ones previous on the line close, leaving back here, this will now be positively charged again and negatively charged in here. So again, these chemicals are not actually traveling very far. This is again microscopic. So these chemicals are traveling that very small space here to here, to the sides of that neuron. They're not traveling down the tube of the inside of the axon. So that is how the neuron can keep the same message strength all the way down the line, because there's not actually molecules moving down it. It's just quickly and very quickly opening and closing those gates that essentially make a wave of a message down through the axon. So let's watch this, and then we'll draw another picture, hopefully make it more so. Make it
Depolarization of an area of membrane causes adjacent voltage-gated sodium ion channels to open. The influx of sodium ions results in membrane depolarization along the membrane. After a short delay, potassium ion channels open and potassium ions flow out, repolarizing the membrane. For the neuron to fire again, the resting membrane potential needs to be reestablished. Sodium-potassium ATPase is used to move sodium and potassium ions against their concentration gradients, reestablishing the resting membrane potential. As the action
So in this image, we can see this is the outside of the axon. This is also the outside of the axon. This here is the inside of the axon. So this is a really good image of what's happening. After watching this, I don't think I'll actually draw it, because the first time I did this and tried to draw it, I did not do as good of a job as I expected. It's hard to draw with a mouse. So again, inside of the axon right here, this is that membrane. These are those gates. This is the outside of the axon.
potential moves down the axon, ions are diffusing only a short distance, allowing the signal to move quickly. At the axon terminal,
So let's watch that again. I'm actually going to slow that down just a bit as we watch that section.
as the action
So what we see here is, let's pause it right there. All right, so what we see here is this glow is indicative of that message being sent. So as that message is connecting and activating the next gates along the line, we have the positive charge on the outside and the negative charge on the inside. Then the message gets there, these gates open, the ions travel to the other side into the interior of that axon, changing the charge to the inside to positive. And so that will then, that change to positive on the inside opens the next gate. So that's why it's a wave. And then after this message passes, the ions leave again. This can happen so quickly. Neurons can fire many thousands of times a second. I think in a later slide, I have the maximum activation time listed. So we'll get to that in a minute.
The electrical impulse passes to another cell at a cellular connection called a synapse. The space between the presynaptic neuron and the postsynaptic cell is called the synaptic cleft. The presynaptic neuron contains signal molecules called neurotransmitters that are packaged inside vesicles. When an action potential reaches the end of a neuron, neurotransmitters are released by exocytosis from the neuron into the synaptic cleft. Neurotransmitters bind to the adjacent cell at receptor sites attached to ion channels. The channels open, allowing the movement of ions into or out of the effector cell, which alters its membrane potential, thereby transmitting the signal from the neuron to the effector cell.
So with that, that showed you the synapse, the place where the axon of one neuron is talking to the dendrites or the cell body of the next. So an axon can touch either a dendrite, well, I'll change that. It doesn't actually touch. It's just very close to allow those chemicals to pass in between them. And there's chemicals that just sit in between them at the synapse too. So the axon's either touching the dendrites or the cell body of another cell. And that's how it gets the message. And you can see this network of cells all sending a message to this neuron, which then gets an action potential, sends it to another down its axon branch. Potentially, that axon branch is touching 1,000 other neurons. All right, so that is good there.
Nerve impulses move very.
So let's go back to the slides. And the reason this is important, so, oh, I do have to share my screen again, don't I? All right, so the reason this is important, the reason we want to know about how these neurons work is because this is the basic process for how we do essentially everything in our entire lives. So it's the process by which we think, it's the process by which we remember things, how we love, how we perceive the world, how we experience things in life, how we create ourselves, and how we live day to day. So that process right now within your neurons is happening countless times. So that wave of sodium, potassium ions going through your neurons, just the fact that you are seeing or hearing or smelling anything right now, this process is happening currently. So these basic biological functions are essential to all other aspects of human psychology. And they're really important to different aspects of how we perceive emotions, how we perceive things in the world. So going back to infancy, in the first years of life, major changes are happening to the neurons and the brain. So again, there's still new neurons being created. So new stem cells are still being created into neurons. They're migrating to where they go. And at this time, there's tons of new axon branches being made, new dendrite branches being made. The brain is trying to link up with itself. Myelination is also happening a lot. It's happening very quickly in infancy, and then it slows through childhood, and then it slows a lot in adolescence, but it doesn't actually finish myelinating your brain until about age 23. So you may have heard someone say, for example, that your brain isn't finished forming until you're about 23. That's what they're talking about. Your brain hasn't finished myelinating until about age 23. By about age 2, essentially everything is where it should be. All the cells themselves are where they're supposed to be. There's a little more change after, but it's very limited. It's not till 23, though, that this myelination that, again, speeds up different processes, makes the message more clear and faster. That's not finished till about age 23. And that has a dramatic impact on things like your planning, your risk-taking potential, a lot of things. We'll get into that in a lot more detail as we talk about adolescence. But that is what we're talking about when we say your brain's not fully formed until about 23. It's the myelination that's not fully formed until about 23. But it does make a really big difference. So during this time in infancy, again, there's lots of connections between neurons being made. There are about two times as many neural connections made than are used. So there's so many connections being made, not all of them are being used, and each neuron, I mentioned this a little bit ago, each single neuron, so its axon branches, can be connected to as many as 1,000 other neurons. So that one message from one neuron can go to 1,000 other neurons. And so that network of connections, so this one neuron might have been connected to 500 other neurons that are connecting to it. So those circuits are really complex. And the circuitry of all these different neurons talking to other neurons are what give us our ability to do things like remember, to think and plan and think ahead. So it's a very complex system in our brain. So with that, when we're infants, we make tons and tons of connections. And then over the next couple of years, we prune away the dendrites that are not needed anymore. So let's say we have this neuron and it's got 3 main dendrite branches right here. Let's say that these two branches are not really getting signal. So, well, the cell, it wants to conserve energy. It doesn't want to waste energy. So if it's not using these branches, it will just reabsorb them into the cell. So then it's being more efficient. It's only using these 3 branches because they're the only ones that are getting messages ever, and it gets rid of those. If it's only using, let's say, these axon branches, it'll get rid of these. It'll reabsorb them into itself. That's not to say that in the future, new branches cannot be created. Just like I talked about earlier with the muscle cells, if you start using those neurons in a different way, they will grow new axon branches, they'll grow new dendrite branches, they will connect to others in the network. So it's pretty impressive. That is called brain plasticity. So let's actually watch another video showing some dendrites and axon branches being extended and created. Created is probably the wrong word there. Some new dendrites as well as axon branches being developed, because it's not whole new cells. The cells exist, the neuron exists. It's just growing out a new branch from that axon or growing out a new branch of dendrites. So let's watch that short video, and then we'll come back to this. So it's on that same page as that stem cell. It's right here. So this is also showing vesicle trafficking. Don't worry about that at all right now. So you can see here is a neuron and a lot of branches. One of these is its axon, and all the rest are dendrites. Here's another neuron. There's some in the background. So watch, it will kind of highlight branches that are growing out and then coming back, as well as axons. So keep in mind these minutes. So this is 6 minutes, 20 seconds. So you can see how quickly your body can create new axon branches. So it's highlighting here that this branch is developing. It's growing new branches. It's reaching out to new neurons. And you can see how quickly that happens. And it's pretty dramatic. So again, this is microscopic. This is not in the scheme of size, it's literally smaller than I could like put my fingers as being close together. So, but it is dramatic. So these neurons can talk to new neurons pretty quickly. We can make new connections very, very quickly within our brain. And so the more you use different aspects of your brain, the more quickly you'll start to use those networks. As another example, I used the example earlier of when I started lifting weights recently, how the neurons, the axon branches, it grew new branches to talk to new muscle cells. So the muscle cells were there, but they weren't being activated. There weren't any axon branches telling these muscles to, hey, activate, contract. And so as I had more of that connection, I was able to lift more weight. So another thing that can happen is I learned French in high school. Kind of, that's debatable. So I tried to learn French in high school. That's more accurate. So there were some things that I remembered still from French. I could count to 10, for example. Not much though. Recently, I started using Duolingo to learn French. And so those same neurons within my brain that I used to use for French, they were getting reactivated. They were probably doing other things with language. With English, I know English and a little bit of French. So those neurons were still doing things. They just weren't networked together with the other neurons that were responsible for speaking French. So as I've relearned recently, it's become easier and easier. It's become, I haven't had to think about it as hard to say certain words or use certain grammar rules. And that's because of this neural plasticity. That's because these neurons that are in these networks responsible for speaking French for me are making new connections. They might even be, because of the structural neurons that are in place in our brains, it might actually even be the same exact neurons that I was using in the past for speaking French. And some other neurons might have respecialized now and they're responsible for speaking French that weren't before. So it's really impressive. And this plasticity, this ability to grow new axon branches and new dendrite branches, means that we can make connections with other parts of our brain, even all the way across our brain. But usually it's in like the same close area that most of that plasticity is happening. So that is very important for us to do essentially anything in our development. So hopefully you understand that, and these examples have made it clear. Messages can come into the dendrite, go down the axon. Hopefully you understand the action potential a little better, because it's very important for everything else we're going to talk about the rest of the course. So let's talk about structures of the brain, like the major structures. Again, these are all made up of neurons, but the areas of neurons are responsible for different things. So we've got things like the cerebral cortex, which is the outer layer. We've got an inner layer of the brain that houses things like the amygdala, which does things with like fear, thalamus, hypothalamus, medulla, cerebellum. So back here is the hindbrain, medulla, cerebellum, spinal cord. Those are responsible for, well, that's actually on the next slide. Let's just go to that. So the hindbrain is the oldest part of the brain evolutionary wise. And what that means is that this was one of the first parts of the brain that evolved in our evolutionary past. And so because of that, it's responsible for very basic functions. It has things like the medulla, which controls vital functions like the heartbeat and breathing. You hopefully don't have to consciously think to make yourself breathe, right? Your medulla is doing that. It's been in place for hundreds of thousands of billions of years, right? I don't know the exact time frame, but it's been there a long, long time. Rats have this part of their brain. Lots of animals, especially all mammals, have this part of their brain, the medulla. Snakes have this part of their brain as well, this hindbrain. And different animals have basically further and further evolved areas. But this is the oldest or lowest part of the brain that contains things that do things like balance, making your heart beat, coordinating your movements. So, oh, here we go. I actually have the date here on the slides. I should have just looked and seen that I had that listed. So it evolved more than 500 million years ago. So I think I was a little over exaggerating a minute ago. The date I said might have been before the Earth was even a ball of rock capable of sustaining single-celled life. Anyway, things like alertness, basic survival. So on top of that, essentially, between the hindbrain and the forebrain is the midbrain. It's a connection point. Lots and lots of sensory signals come to the midbrain. Information from your eyes, from your ears, your pain receptors can come here. There's a lot of long axons here that go to other areas of the brain that can go to your prefrontal cortex, go to your visual cortex, those kinds of things. So this midbrain is the next oldest part of the brain. And so lots of other animals have this. I believe snakes also have a midbrain that looks really similar actually to ours. Rats have a very similar midbrain to ours. So you can think of that as like these creatures evolved over time, and then at the splits of the from the point where we had mammal-like dinosaurs, essentially, there was kind of a split there, and those mammal-like dinosaurs then evolved into birds, and their brains evolved to different things, versus humans evolved from these mammal-like creatures way back in evolutionary past. I keep thinking of the dinosaur Dimetrodon. I actually learned at the Ogden Eccles Dinosaur Park. What's it called? Yeah, I just call it Dino Park. That's where I say, hey, do you kids want to go to Dino Park? And they're like, yes. But yeah, the Dimetrodon is a human ancestor way back, which I thought was pretty neat. All right, so forebrain. That was way off topic, but that's okay. Pretty interesting information. The forebrain is the most highly evolved portion of our brain. It contains the limbic system, the thalamus, the basal ganglia, hypothalamus, and the cerebral cortex. The cerebral cortex is the outside wrinkly portion that you can see. So here we've got thalamus, hypothalamus. Corpus callosum is actually just a big bundle of axons sending messages from your left side of your brain to your right side of your brain. So let's break this down. Limbic system. Oops, I went backwards rather than forwards. So limbic system does a lot of emotion, memory, contains the amygdala, which is important for survival. Hippocampus is very important for memory recall as well as storage. If your hippocampus is damaged, it will be very hard to create new memories or recall previous memories, but the memories themselves are not stored there. So in actuality, and we'll talk about this in the future too, in actuality, we did just talk about neurons and neuron circuits. In actuality, a memory is essentially your body and your brain reactivating the same neurons that were active during a memory. So think to something that you can remember really well. Let's say it was your high school prom, maybe your first kiss, maybe those two things coincide. So think back to your first kiss. As you remember that, you are literally activating some of the neurons, probably not all, almost certainly not all. Some of the same neurons are being activated as you remember that event as when it actually happened. So you might be able to remember the smell of your partner. You might be able to remember the sounds that were going on around you, those kinds of things. So think back to your first kiss. You are literally reactivating the same neuron circuit or at least part of the same neuron circuit when that happened. And that is a memory. It's not a single neuron that's holding this memory of your first kiss, and you have to activate that one neuron to remember that. You're activating this whole system of neurons, which is also why you might remember similar things too. So if you remember the first time you learned to drive, and then you remembered a time when you had to learn to drive a new car, some of those memories might be the same and similar and connected to each other because some of the neurons within those circuits are actually shared. So interesting thing. So the hippocampus directs like activating that circuit of memories. It's pretty neat. Thalamus is basically a way station that takes a lot of sensory information and sends it out to different parts of the brain that needs it. Basal ganglia is very important for movements, especially habitual behaviors. So me, for example, I keep my phone in my left pocket. So it's a very habitual behavior when I hear a ding or something to reach into my left pocket, pull out my phone, and then click the fingerprint reader on my phone. So that is now a very habitual behavior. I have a system of neurons that's kind of governed by the basal ganglia that just does that really easily, very quickly. This is also one of the reasons when you get a new phone, so let's say I changed from this phone and the fingerprint reader instead was under the screen or something like that. I would have to retrain myself to activate it that way. I would probably the first, 20 times, and even when I'm not paying attention after that, pull out the phone and try to activate it like I did my old phone. So with that being said, that is one of the reasons habits are so hard to break, because we have these neural pathways and connections, kind of like those memories. This system of neurons is really used to activating together. So when I hear that sound, even if it's someone else's phone, like if my friend has the same phone, that happened to me the other day. One of my friends had the same tone as one of their notifications, and I checked my phone. Even though I could hear it was coming from over there where they were sitting, I still went to check my phone because those neurons were so used to activating when hearing that sound. It was just a habitual behavior, just happened. So yep. Hypothalamus monitors a lot of the reward system within our brain. So eating, drinking, emotion, stress, reward, sex. But with that being said, it is not the only pleasure center of the brain. There's a lot of those pleasure sensations that are responsible for monitoring there, but it's not the only one. All right, the cerebral cortex, again, that outside wrinkly bit. So if you were able to touch your brain, like take off part of your skull and like touch, you would be touching the cerebral cortex. It's that outside wrinkly part. It's the newest in terms of evolutionary time. And it's split into the occipital lobe here, and that does a lot with vision, temporal lobe, a lot of language, parietal lobe, and motor and sensory cortex. Obviously, motor and sensory cortex, sensation, and then sending messages to your muscles. Frontal lobe, and then at the very front of the frontal lobe is the prefrontal cortex. So, yep, also temporal lobe for memory. Oh, here's a good example. You may have heard of Phineas Gage. So he had a railroad spike, literally that spike that he's holding there, go through his head when he was working at a railroad. Some dynamite detonated when it shouldn't have. It went through his brain, right here through his frontal lobe. So without that frontal lobe, he was very emotionally shallow, distractible, insensitive, wouldn't follow directions, didn't really care about the people in his life as much as he did beforehand. He was very selfish. So the frontal lobe is very important for a lot of the social behaviors that we as humans do. So, all right, so with that, at birth, these areas are already in the process of specializing. So these areas are being responsible for those things. So for example, when an infant wiggles their arms, their motor cortex is telling their arms to wiggle. So it happens very early on. So a lot of research has been looking at how language develops. So we talked about pruning. We showed the examples of new axons and dendrites being grown. This is from birth to 11 years to adult. You can see lots and lots of connections are happening early on in life. And then at about 2 or 3, there are a lot of pruning happening. So our brains make way more connections than we will ever need. But then as we start to have experiences, we start to solidify those connections, and the brain learns, oh, I need to keep these networks, but I never use these networks, so I'll reabsorb those axon branches. All right, so let's talk about prefrontal cortex. We will talk about it very many times. Higher cognitive functions, planning, reasoning, self-control, a lot of self-directed actions that you might take. So let's say, for example, I have that habitual behavior, checking my phone when I hear a tone, right? My prefrontal cortex, even though that habitual behavior might already be sending a signal to the motor cortex, my prefrontal cortex can make a choice and say, no, don't do that. You don't need to do that. Or I'm trying to focus on this conversation. Don't actually check your phone. I know it's your habit, but don't do that. So your prefrontal cortex can do that too. All right, so somatosensory cortex. That is here on the side of your brain, your right side of your brain. So for me, that's this right here, is actually controlling my left limbs. The left side of my brain is actually controlling my right limbs. So that is how that works. Here you can see an image of the somatosensory. So we're talking about sensation here. The motor cortex is right next to it, so still relevant. But the somatosensory cortex is also over here, and it's where you get the feelings from the different sides of your brain. So right here this is about where the sensations for my eyes, nose, and face are. A little bit lower, that's the sensations for my lips on the left side of my head. So literally me touching my lip right now is being sent to the part of my brain right about here. So kind of neat. Similarly, it also shows you that we have many more receptors for, say, the face and the hands than the core. So you don't have very many sensory receptors for your core. You have more for your genitals. You have more for your face, your lips, your hands. Those are the parts that have evolved to be able to sense and feel more delicate or fine or specific features. Motor cortex is in a similar place. You can see this kind of weird image. We've got a lot of the motor cortex devoted to the hands. That's why it's quite a bit easier to learn to, say, play an instrument, say a piano, with your hands than with your toes. You can see there's not a lot of the motor cortex devoted to your toes. One interesting fact as well, jumping back here, looking at where the different senses are in your body, you can see here that the senses for your genitals are actually quite close to, in your brain, where the senses are for feet and toes. So it actually is hypothesized that one of the reasons that a foot fetish is a common thing for people is that there might just be some crossing of wires of signals meant to be going to this area that's responsible for feelings in the genitals are kind of getting crossed with feelings from feet and toes. So interesting just fact about how neurons work and how those networks are connected. If there's a little bit of cross connection there, some of those sensations from the feet might actually be going and ending up in this area of your brain that's responsible for feelings of the genitals, which I just find very interesting, seeing these explanations for human behavior centered on something biological like that. So motor cortex, again, you've got different areas that are devoted to different parts of your body. Very similar thing. There's a lot of space devoted to the hands, a lot of space devoted to the face and the tongue. We wouldn't be able to speak as well if we didn't have so much of the motor cortex devoted to how your tongue moves, as an example. We have this corpus callosum, which is essentially just a bunch of axons. It's an axon highway between the two sides of the brain. So your left and right sides of your brain are always speaking to each other all the time. And a lot of that is going through this corpus callosum. So in undergrad, I had the opportunity to dissect human brains as well as rat brains. They all have corpus callosum, and you can poke the rest of the brain and it's like kind of squishy. But the corpus callosum, when you poke it, feels very hard. And this is because just the density of those axons. There's so many messages being sent between both sides of your brains. It's really impressive. So also remember plasticity, even though these different areas of the brain are responsible generally for those things. So your temporal lobe on the left side of your brain is mostly responsible for understanding language. If that area is damaged, say like Phineas's gauges or from a head injury, something like that, the rest of the network that was connected to that can actually specialize. And so that area of language, even though that's damaged, you might now be processing language with this part of your brain. Your brain is plastic enough to do that. It does a better job the earlier on this happens. So for children that get brain damage, they tend to have a better prognosis, be able to regain those capacities than say if an adult had that same kind of injury. All right, so the last part of the nervous system that we'll talk about is the endocrine system. It's a system of glands that regulates the organs by releasing chemicals into the bloodstream. So glands are the organ or tissue that create the chemicals, and those chemicals that they create are hormones. So we've got hypothalamus, pituitary gland, those are both in the brain. Then we've got pineal gland, also in the brain, thyroid, thalamus, pancreas, adrenal glands, placenta, ovary, and testicles. They all also make hormones, but they're outside the brain. But they are part of the endocrine system and part of your nervous system. So, and they're connected through the hypothalamus within your brain. So the endocrine system is a lot slower than neurons, because what it's requiring is for any of those glands to create those hormones, then that hormone has to flood your blood throughout your whole body system. So that has to get pumped through your heart to get all around your body. But it is interconnected with the nervous system. So again, the nervous system is those really quick neurochemical reactions and signals through neurons when these different sensors within your body then send messages through the hypothalamus. Then it is also in your conscious perception. So stress hormones flood your body and you're conscious of that happening. So why do changes in the brain occur? So especially with early experience, it's mostly driven by experience, by seeing things, by sight, sound, smells, touching. So that is why play is so important for infants. You don't need really special toys. Think of our evolutionary past. What would we have in our disposal? We'd have other people, we'd have very simple objects, hopefully multiple colors. So giving children a variety of very simple toys. So think of the toys you might find in, say, the like before preschool or like nursery area of a store. Those really simple ones, blocks, stackable things of different colors, things that make sounds, rattles. All these are really great toys. and it helps the brain start to make those connections because it's making connections, but it helps the brain solidify those connections. So that's why it's so important to do play with young children. All right, and now let's also talk about sleep. I think I might actually make this piece one of its own videos because it's really relevant to a lot of my classes on psychology. So I might actually just stop here and have this, well, your video will continue, but I'm going to use this as a piece in other classes as well. All right, so we just talked for quite a while about neurology. Now let's jump to talking about sleep, cognitive development of infants, and a little bit about language development. This is all going to be a little quicker because the most important thing I want you to remember from chapter 3 is the neurology, but these pieces are also important too. So newborns sleep a lot, 16 to 17 hours a day at first, and then it drops down to about 10 and a half hours at about months 3 to 7. One thing to be aware of is SIDS for infants. It's sudden infant death syndrome. It's when an infant stops breathing seemingly without cause in the night and dies because of that. So that risk is much, much lower later on in the child's life. So as they get to age 1 and age 2, it's much, much lower. The risk drops off a lot after 8 months. So some recommendations are place babies to sleep on their back. Don't put them to sleep on their front or their side. Don't have lots of pillows and blankets in the bed with them. Having the room a little cooler helps as well. And bed sharing is a high risk factor. So that can be a hard one because let's say for mothers, it can be a lot easier if you're breastfeeding the child to have the child sleep right next to you. And in the middle of the night, feeding is a lot easier of a process. Then you can go to sleep while they're feeding. They can go to sleep right afterwards, but it does increase the risk of SIDS. So there are different kinds of beds that can be attached next to your bed. Where the baby has their own space that's clear of any obstructions that could increase the risk of SIDS. So that's that kind of cost benefit. What is a higher risk? What do you think is the most appropriate way to do that? It is just something to be aware of. With that being said, breastfeeding does still seem to be the best. The modern day formulas are much better than they used to be, but breastfeeding still does seem to do a better job at developing a young child's body as well as brain. So some parents can't breastfeed or can't produce enough milk or don't want to, aren't able to with their work schedules. So with that, that is fine. Formulas that we have today are very, very good. There's also a lot more options to buy breast milk like online. You can order it from other people as well. So with that, most studies for the usefulness of breast milk are correlational. So there's not a lot of causal material about breast milk versus formulas. So it's hard for a study to get approved that says, hey, we are going to make these people only breastfeed their babies and we're going to make these people only bottle feed their babies. So that can be a tough thing to get past an IRB. So most of this is people who have done one or the other or both at different places. So definitely watch this video for more detail. We're not going to cover that right now in this recording, but it could be a good piece of information for more detail about this topic. So motor development. So infants develop motor skills for what they're perceiving, what they're acting around, what they're trying out, essentially. Basically, babies try out different motor skills, and the ones that work stick. So reaching and grasping behaviors, as those work, they stick. Those neuron connections for those motions of reaching out, grabbing a rattle, bringing it back to their mouth, that all works. They get those sensations. They're successful in those. So those connections stick. So this is all dependent on things like neural capacity, physical capacity, and their perception to determine what's possible for a baby. So if a baby has fully functional neural capacity, but they don't have the physical capacity, maybe there's something wrong with their elbow, or they have an injury or a deformity on their arm, and they can't actually like reach and grasp, well, those neuron connections won't be solidified because it's not a motion that's actually working for them. Maybe for their other arm, it will just fine. But this also goes into what you should do to interact with babies. So if a baby sees something, they will attempt a variety of different ways to interact with it, whether it be just staring at it and looking at it, whether it be reaching towards it, later on crawling, kicking, swinging arms. Infants put skills together to develop motor function. So one really big recommendation is just to play, just to let infants play as much as they're awake. Let them be doing things. That can be really hard in the middle of the night. And so feel free to sleep, obviously, when you need to sleep. But letting them play is the best thing. Don't just stick them in a carrier and let them be there when they're not crying. As an example, I had a professor who was teaching a parenting class. And so it was for low-income people to learn how to parent better, some skills and things like that. One thing that she noticed is that when they came into this room, like in a classroom setting, they left their babies just in their carriers. And so at the end, she asked them, hey, why did you all leave the babies in the carriers? And they're like, well, they weren't crying, they weren't disrupting anyone, so I didn't want to bother other people around by like taking the baby out and playing with it. And I mean, seems very respectful and for the people around them. And some of the other people were saying, well, they weren't crying, so I didn't want to try and play with them. They might get upset, then they might distract other people. But also, I'm so tired because I'm working 2 jobs that I just like to let them sit unless they need something. But the thing is, those babies, all of those babies did need something. They all needed that interaction. If they're awake, they should be playing in some way, right? So very respectful of them to not want to disrupt all the other people in the room that are trying to listen to the lesson. I'm not trying to say anything about that, but it's a really good example of, well, even though the baby's not crying and not saying, hey, I'm hungry, or I have a poop, or I want to go to sleep, they still do need to play and build those sensations, build those perceptions, be able to try out different movements to learn. That's really what their brains need. So reflexes are an inborn built-in reaction to stimuli. So one example is the rooting reflex. If you touch a baby on, say, their cheek or anywhere close to their mouth, they will turn their face towards and try sucking that object. It's a good survival instinct that has genetically, and it has survival value, so we evolved that. So that's the rooting reflex. The sucking reflex, if you put something in their mouth, they will try to suck on it. So hopefully that's something like a nipple or a pacifier and not a Lego. So when you have an older child and a younger child, you might have to be more worried about the Lego thing. I'm sure parents aren't trying to put Legos in their parents' mouth or in their kids' mouths. So my favorite reflex is called the Moro reflex. When startled, a baby will flail their arms and their legs out and quickly try to grab at anything around them. So when they're very, very young, this Moro reflex is essentially you spook them and they go, ah, and try to grab things. It's my favorite because it's hilarious to watch. And maybe that makes me a terrible parent and a terrible person, but it is really, really funny. So I would sometimes do that with my children when they were very young. I would go, boo, or something, and watch them do that. And then I would get a dirty look from my wife, and I would laugh, and I would do it again another time because it was just reinforcing enough to see that funny surprised face from the baby. But basically, why this exists is far back in our evolutionary past, it made sense for the baby to flail out because it allowed, say, a mother to then grab a baby as it was falling out of their arms or out of a tree. It made it easier or slowed the descent of a baby. So even if they did fall, they were more likely to survive. So it just shows how this evolutionary biology affects current human behavior. So really interesting. So gross motor skills are those things requiring large muscle groups. So the core, the arms, the legs, those kinds of things. So moving, walking, trial and error helps children develop these. So you can see the graph in your book and right here on the screen. This is about when you can expect these things to happen. It might be a little earlier or a little later for your own children or for yourself in your life. So, but that's kind of the general guidelines. Fine motor skills are those finely tuned motor motions like hands, feet, grasping blocks, using a spoon, manipulating buttons. And so those develop later and they're harder, but they also, the fine motor skills really help with the cognitive development at the same time. So being able to make a stack of blocks will really help with cognitive development in a young child. So If you want to know more about that, this is a really great video. It shows kids at a couple different levels of development of their sensation, perception, and motor ability, both gross and fine motor ability. And you can see some differences in their cognitive abilities as well. So let's talk about sensation and perception really quickly. Sensation is simply the information coming in. So it's going to your receptor, your sensory receptor cortex, right? So you're getting things from your eyes, ears, tongue, nose, skin. Perception is, okay, now that I have this raw data, this light from seeing things, now that I have a pain sensation in my hand or something, what do I do with that? What is the interpretation of that? What do I perceive is actually happening? Well, looking in front of me, I see, I'm in the garage office today, so I see my child's bike, I see a wall, but I mean, really, that's just light data entering my eyes, right? So that's a sensation. The perception is, oh, I perceive my daughter's bike is hanging over there. There's a license plate over there, those kinds of things. Are we seeing a color, a shape, a pattern? So infants can't report what they see and hear, just like I just did. So a lot of behavior, a lot of research has to look at behaviors to figure out what can infants perceive. So one of the main ways we do that is a visual preference method. What is an infant looking at more? If you bring in something new, but that's really similar, do they perceive the difference between those two objects? Let's say something slightly, a toy that's green and slightly taller versus a toy that's teal and slightly shorter. Can they perceive that difference, or does it seem like the same thing to them? So that's what you do with habituation and dishabituation. Let's say you take that original green toy, let's say it's just a pyramid or something, and you put it in front of the child. You present it to them till they stop staring at it. They're not interested, or it seems that they're not interested anymore. Then you present a new similar stimulus, a smaller pyramid that is teal instead of the same green. So you see, well, do they now pay attention to that new thing more than they were paying attention to that old thing? Can they perceive there's a difference there? So that's one way to check that. Eye tracking is another way. This is a machine that can track the eye movement of children. You can strap it to their heads or just have it across, like looking at them. And from that, you can get a heat map of where exactly is a child looking at, for how long, those kinds of things. So what do infants see? Well, again, it's really difficult to tell this for sure, but it seems like they're very nearsighted at birth, and that might be because sight is one of the least developed senses at birth. That's because the eyes aren't really seeing much difference inside the womb other than light and dark. So the eyes haven't really had a chance to connect up and perceive and sense a lot of different things. So this shows, we suspect this is about what a 1-month-old sees versus 2-month-old versus 3-month-old versus 1-year-old. So at about 6 months, you've got, as an infant, about 20/40 vision. So I think that's actually better than my vision, without contacts, that is. So infants can't perceive occluded objects, so they wouldn't be able to perceive that this is necessarily a cat back there. They can start tracking partially occluded objects at about 3 months. Depth perception happens about 3 to 4 months old, and that is also about the time that crawling happens. So it seems that that ability happens cognitively around that time. The linking up of neural networks seems to coincide with the time that their motor development is capable of helping them crawl. So 6-month-old is not likely to crawl out onto the glass of this kind of experiment where there's a visual cliff there. Like, this is plexiglass, they're not actually going to hurt themselves. But earlier than 6 months, you might see a child just crawl out with no problem at all. Like, they're not even afraid that they're going to fall. So watch that video if you want to see some examples of this. There's a couple other similar visual cliff examples in that video. So for hearing, fetuses in the last 2 months can hear sounds in the womb. They might even be able to recognize the patterns of sound of people speaking. So they might not be able to recognize the actual tone of your voice because it's different inside essentially the womb, but the pattern of how you speak, they might be able to recognize that. They're very, very, very attuned to human speech, mainly because we have evolved the capacity to speak as humans, and we have evolved neural capacities to pick up on different things like pitch, timbre, volume, rhythm. So with that, we are very well in early childhood and infancy programmed to pick up on language quickly. So this is also why learning a new language is much easier for an infant than it is for, say, me, an adult. Learning French is very difficult for me versus my daughter is in a Spanish immersion program and she's picking up on it very, very quickly. A lot quicker than I would being immersed. So it is hard for infants to hear soft sounds. So whispering very quietly can be very difficult for infants to hear. So speaking a little louder, like at normal inside voice volume or slightly louder, can be beneficial. You don't want to yell at an infant, hopefully you don't want to yell at an infant, but they do have a hard time hearing very soft sounds when they're first born. So intermodal perception is integrating information for one or two sensory inputs. So things like vision and hearing at the same time. So seeing someone talking to them and hearing it, that develops over time to be able to point out where that happens. So again, this all comes back to the point, the best thing to do for a baby is to interact with that baby. Talk to the baby, play it music, tickle it, move its arms around, let it experience different sights, smells, sounds, let it try to manipulate objects. These are the best ways to play with a very young infant. So let's jump to cognitive development. Piaget had a popular stage theory. As we talked about in our first week, we see that most development is pretty continuous. There's some examples of discontinuous that we even talked about today with the growth, the discontinuous growth spurts. So some of what Piaget, some of his observations were really useful, and we still use some of those, but his actual stage theory is not so useful anymore. But some of the observations were really good. So let's jump to this. So now researchers investigate specific processes that we do cognitively. So how do we speak? How do we remember? How do we form memories? How do we learn a new thing? That's what cognitive researchers now look at. There's no real overarching theory exclusive to cognitive development. So it's more focused on general development, the brain, and neuroscience. But one of the biggest things, one of the biggest subjects in cognitive development is attention. Attention is just that focusing of your mental resources on something specific. And when you do that, it improves your cognitive processing. So if a child is focused on a green block, they will then perceive that green block better. Like something that they're interested in, they'll hold attention on it better. So basically we understand and perceive things better when we are attending to them. So if there are two conversations going on in a room, the one that you attend to, that's the one you'll gather more information from, right? So with that, imitation is another thing that infants do. So they can imitate facial expressions soon after birth. So with that, they're seeing, perceiving, trying things out. Imitations of actions and behaviors is very important in learning. So seeing you grab things, seeing you manipulate things, seeing you talk, hearing you talk. This is very important for learning and cognitive development. Memory is very interesting when we're talking about cognitive development, especially with infants. Just like these other networks, we have these neurons up until the age 2 that are still growing tons and tons of axon branches and dendrites. But until they make these connections and figure out how the body works, memories aren't really being formed because those networks aren't in place yet. So memory is that retention of information over time. Implicit memory is things that we remember without conscious recollections. So like how we use a spoon, that is not something I have to think about consciously anymore, right? Explicit memory is usually what we're thinking of when we talk about memory, and that's memory of facts and experience. So we mentioned earlier a first kiss. That memory is an explicit memory. And that's generally what people are talking about when they're talking about memories, but also those implicit memories are memory as well. So how to do things like ride my motorcycle or use a spoon, that's implicit memory. So most research suggests that explicit memory doesn't really exist until about 1.5 years old. So probably the earliest memory that any of you watching this right now will have would be about age 2. So it can be a little earlier, but that's generally about what it is. For me, my earliest memory is actually about 4, but I also have a poor memory anyway. I've met some people who do have memories up to about, or the earliest is about like 1.5, which is pretty impressive. And the reason for that is these neural networks that are connecting your visual cortex to your auditory cortex, the sensory motor cortex, all of those connections are in infancy still figuring out how things work, how to interact with this world. And so as it finally gets all connected up, then you can start developing memories. Before that, you really can't, or they don't remain for a long period of time. So why can't you remember when you were 2, or why is your earliest memory not earlier than say 2.5? Mainly because the prefrontal cortex was still making connections and learning how to create those long-term memories. So it's not that anything's wrong with you. That's a pretty common thing. For me, like I said, my earliest memory is about 4. I've met people whose earliest memory is about 1.5, but you won't really go previous to that. So language development. Language is our communication through symbols, spoken, things like that. So this is a little chart of basically what happens. And language is a really good example of a continuous development process. So first, a baby will coo, try to make sounds, make noises. They might start to understand their first word at about 5 months. They might start babbling, trying to make similar sounds at about 6 months. They change from that to learning specific language sounds. So they're starting to differentiate if they're hearing more than one language in the home. They're starting to use gestures around a year old. They might speak their first word just after a year old. They start to get bigger vocabulary after that. And then they start speaking short 2-word sentences, 3-word sentences, 5-word, 7-word, and then on and on and on. So it's a really continuous process that goes from this general making noises to being able to speak. So language development is something that we are very well programmed to do. Those areas of our brain are really well attuned to doing that early on in infancy and early childhood. So I had a professor that they spoke French. Their wife spoke, I believe it was both Russian and Ukrainian, but I think they were teaching their children Russian. So when he was with the children, he would speak only French to them exclusively ever since the time that they were born. When he was alone with any of the children, he would only speak French. Similarly, his wife would only speak Russian to them at any point in time when she was alone with them. Still, even to this day, they do that. But then when they were together, they would speak English to each other as well as to the children. And so these children, because he was also a cognitive psychologist, so he knew a lot more about language development than I did, or than I do. So those children became trilingual just because they have that natural capacity to learn language. Whereas if you put me in a setting with him speaking French and his wife speaking Russian, I would understand maybe like 10% of what he said and absolutely 0% of what his wife said. And even I could live in that house 4 years and I would probably gain much less than those infant children would in 1 year. So with that, around 100,000 years ago, we had the neurological developments that made it possible for us to speak with language, to use words and have very specific sounds like that. We've got a couple different areas of our brain that are important for this, Broca's area and Wernicke's area. There's also a suggestion that we might have a language acquisition device. So Noam Chomsky, which is a great researcher and good philosopher as well, studies the possibility that humans are pre-wired to acquire language, which it does seem to be the case. We have the capacity, the neural capacity to do that, and we quickly do pick up language. So with that, also patterns of learning, like how we learn English, is very similar to how people also learn Spanish from infancy, as well as how people learn Chinese, or so let's say Mandarin Chinese, versus how people learn any language. They're really, really similar patterns. The way that we go through the cognitive process of learning a language is really similar across languages. So do we have a neural pattern to learning language? Seems to be the case. So there's also environmental influences. So talking to a child dramatically improves their language retention. Reading to them, trying out different grammar, using different words, the more words and grammar they're exposed to, the better. So studies have been done that show that children who are hearing more words a day, so like 300 as compared to 700 words a day, will have a much higher cognitive capacity, better memory, better ability to do math far in the future. So doing things like child-directed speech and speaking to a child a lot is very important. So child-directed speech is very similar to baby talk. So it's a higher pitch, a slower tempo, it's exaggerated, and many cultures and languages do this. So when you're talking to a child, you probably hear maybe parents or other people speak to them differently. Say, I'm going to imagine there's a baby here. It's honestly going to be pretty embarrassing to watch myself on a video do this later on, but maybe it'll get a laugh from you, and that's not bad either. So let's say there's a baby here. I'd be, oh, how are you doing? Oh, look at your little hands. Look at your little feet. Here's a block. Do you want to play with it? So a little slower, a little higher pitch, a little bit exaggerated with the way I'm speaking. That's child-directed speech, okay? Another aspect of it is correcting and encouraging words and sentences. So as a child gets some words and they might say, dog bark. You say, oh, did you hear the dog barking? And you repeat the sentence in actual correct grammar, as long as you've got fairly correct grammar. I don't know that I always do. So, but that is some of the best ways to help a child learn language. And parents tend to naturally do these behaviors when they are just interacting with their children. So with that, do these things naturally. Have it just be a part of what you do with the child. Be an active conversational partner. If they're just making noises, respond to the noises. Act happy. Say, oh, did you want some food? Are you sleepy? Things like that. Be conversational, even when they can't actually use words. Narrate your daily activities. So when the baby is there just with you in your room, say, hey, I'm working on the computer. I'll give you something in a minute, or I'll give you your bottle in a minute, things like that. Slow your pace. Don't feel judged by other adults when you're talking to your baby like this. This is for the baby. This is really good for them. So even if someone else is looking at you funny, or students are laughing at you for talking in a really funny voice, just do it. It's important for the baby to learn that way. Use more gestures, play games, and listen, especially as they're starting to make noises and respond back to you. Listen to what the baby says and try to elaborate on that. The dog bark example, oh, do you hear the dog barking? So these are some of the really critical things to happen with infancy. So play, just normal play, interact with the baby as much as you can, speak to them as much as you can. These are some of the critical pieces to remember going forward. And so that is the end of chapter 3. I know this lecture was a little longer than some of the other ones. It's because I really wanted to go into a lot of depth on the neurology that we're covering, because it is very important both for this cognitive development and language development. You're making hopefully connections there, as well to other socio-emotional aspects of development here and in the future of the lifespan. So thanks for watching this lecture on chapter 3. Don't forget, you've got discussion board posts due on, and also things like smart books to do. So make sure you're checking your schedule and getting those done at the proper times.